Welcome to this explainer. Have you ever actually stopped to wonder how a simple tap on your phone instantly pulls up a web page from a server literally halfway across the globe? It's wild. The modern internet connects billions of devices seamlessly, moving mountains of data in mere milliseconds. Well, today, we're going to put you in the shoes of the ultimate network architect to solve the incredible puzzle of how these computers actually talk to each other. And we aren't just going to look at some dry theory. No, we're going to build the entire system from scratch, together, step by step, to uncover exactly how the OSI model works. Let's dive right in.
So, let's just strip everything away for a second. Imagine you've got exactly 2 computers in the entire world and you want them to communicate with one another. What's the absolute most basic, fundamental way to make this happen? Well, to start, you'd probably just grab a physical wire, plug one end into the first computer, and plug the other end into the second. Boom! Then you'd program those computers to send electrical pulses through that wire, representing simple zeros and ones. And hey, this isn't just theoretical. This exact same concept is literally what's happening right now inside the copper wires in your walls or those massive fiber optic cables running along the bottom of the ocean.
And just like that, congratulations, you've established the foundation of communication, the physical layer. Whether we're talking about a standard Ethernet cable plugging into your router or the invisible radio waves of your Wi-Fi network, this layer is all about raw hardware transmitting those electrical pulses. You've basically created a system to send physical signals from point A to point B. It's simple, it's elegant, and it works flawlessly for just 2 isolated machines.
But, of course, as your tiny network grows, a brand new problem emerges. A third computer enters the picture and it wants in on the action. So you wire all 3 of them together and start sending those electrical signals again. But almost immediately, you hit a brick wall. There is absolutely zero way to understand from whom a message is being sent and to whom it's actually intended. It just turns into this chaotic mass of zeros and ones bouncing around the wires with no clear direction.
Right. So you clearly need some sort of identification system to fix this. Cleverly, you decide to introduce a unique identifier for all 3 devices. Now, whenever data gets sent across the wire, you make absolutely sure the message explicitly mentions its source address and its intended target address. You've essentially created digital name tags for your hardware. In the real world, we call these tags MAC addresses, and they're literally permanently burned into the network interface card of your device right at the factory.
And just by establishing these rules, you guessed it, congratulations again, you have just built the data link layer. By ensuring that data can actually link up to the correct physical device using those hard-coded MAC addresses, you've completely solved the local traffic problem. The computers on your small network can now easily identify each other. You're making some incredible progress here, but our world is about to get much, much bigger.
Yeah, because another problem just reared its head. Your network is wildly successful, it's growing like crazy, and suddenly, you don't just have 3 computers anymore. You have around 1,000 computers scattered all over the world, and every single one of them wants to communicate with the others. The complexity of the whole shebang just skyrocketed.
This perfectly illustrates a massive scaling issue. The traditional approach you've been relying on so far, connecting every single computer physically with the wire and broadcasting messages to all of them using source and target MAC addresses, well, that simply wouldn't be feasible anymore. The sheer amount of wiring, plus the deafening digital noise of every computer constantly shouting to every other computer, would totally break the system.
But, clever as you are, you realize you need some serious organization here. So you decide to group computers together, maybe by region or local network. You assign a completely new, unique identifier to each group to build a controlled, logical flow of data for those specific clusters. To put that into perspective, if a MAC address is a device's social security number that tells the network who it is, this new identifier is more like its zip code, telling the network where it lives. Instead of shouting to the whole world, data is now routed logically from one network group to another. You, my friend, have just invented the IP address.
Look at you go. You've successfully given your network a global postal system. This routing magic makes up the Internet Protocol, which is often known as the network layer, and it completely solves the problem of a rapidly growing decentralized web. Data can now intelligently find its way across thousands of interconnected networks to reach the exact right zip code.
But hold on a second, because the actual nature of computing is evolving. Computers aren't just dumb communication machines anymore, right? They do multiple things at exactly the same time. You might have an email app open, a web browser running, and a file transferring, all happening simultaneously on a single machine. That means multiple applications want to jump into the communication stream all at once. So it's no longer just a problem of computer-to-computer communication, we've shifted to an application-to-application or process-to-process communication challenge.
So the real kicker here is how you separate that traffic once it actually reaches the right computer. You decide to introduce yet another identifier, this time specifically for addressing those individual processes or applications running on the machine. You decide to call these new identifiers ports. For instance, you might designate one port specifically for fetching web pages and another one entirely for sending emails. This keeps the incoming traffic perfectly sorted and hands it off to the exact right application.
We can't celebrate quite yet, though. The problem now is that stuffing IPs, ports, and data all together creates these massively large communication payloads. These incredibly heavy payloads now have to travel through routers and complex routing logic all across the globe. This whole process consumes a ton of memory. In fact, a payload that's too large can actually cause data drops, create bottlenecks, or literally damage the memory of the routers they travel through. The system is basically getting bogged down by its own weight.
To solve this heavy lifting problem, you write some pretty brilliant logic to slice your massive data payloads down into smaller, much more manageable chunks, which you call segments. On top of that, you add logic to keep track of these chunks to make absolutely sure they're all transferring successfully and getting reassembled in the right order. Crucially, this includes error checking. So if a chunk gets lost in transit, the system actually knows to ask for it again, making sure absolutely nothing is missing.
Now, you've really earned it. Congratulations again. You have just built the Transport Layer Protocol. Using real-world standards like TCP, this robust system of tracking, slicing, and ensuring reliable delivery guarantees that no matter how complex the app is or how large the file, your data gets transported safely without overwhelming the underlying hardware.
All good and fine. But let's take a quick step back and look at the fragile nature of what we've just built. Because your communications are now depending on multiple stacked layers of logic, you've introduced a huge risk. If any of these underlying layers interrupts for some reason, let's say a brief network drop or a random router hiccup, your entire conversation drops. And worse, there is no way to get the context back. You literally have to start the whole download or communication completely from scratch.
And, absolutely no one wants to restart a giant file transfer when it fails at 99%, right? So you decide to build a dedicated layer of logic strictly to preserve the state and context of your conversation. This way, even if those underlying layers momentarily interrupt, you can still retrieve the context of the current session and pick up right where you left off. By building this dedicated layer to manage the ongoing dialogue between machines, you just earned another massive congratulations for creating the session layer.
We're getting close, but there's still a bit of a gap in perspective. The issue now is that all this stuff you've built so far relies purely on a computer-required data model. Sure, it's highly optimized for machines to move binary chunks over wires, but it is absolutely not in a manageable shape for humans to easily interact with or understand.
To bridge that gap, you decide to build an encoder and a decoder. This incredible tool handles the seamless conversion between the human-preferred data model and the computer-required data model. This is exactly where things like data formatting, compressing a JPEG image, or even data encryption happen, like that little security padlock you see up in your web browser. This ensures that when the final application receives the data, it can actually read it safely and correctly. You have successfully completed the presentation layer. Okay, since you've come so incredibly far, there is just one final hurdle left. You need to wrap all of this up so that developers around the world can actually build complicated applications on top of everything you've constructed. I mean, they shouldn't have to worry about electrical pulses, MAC addresses, or data sequencing every time they write code, right? You need a maintainable, human-understandable standard of communication that acts as the ultimate bridge between the invisible network and the software we actually use every single day on our screens.
So you create text-based protocols to serve as this ultimate standard. These protocols allow software to interact directly with the network seamlessly. This is exactly where protocols you probably recognize, like HTTP for loading websites or FTP for transferring files, live. By creating these user-facing standards, you've officially established the application layer.
By tackling one single, logical problem at a time, from physical wires all the way up to global software standards, congratulations! You have constructed the legendary OSI model layered architecture. You built it from the bottom up, starting at the physical layer, moving to data link, scaling with the internet layer, securing delivery with transport, maintaining conversations with session, translating with presentation, and finally, interfacing with the user at the application layer. In the real world, this actually works through a process called encapsulation.
When you send a message, it travels all the way down this pyramid on your device, shoots across the physical wire, and then climbs all the way back up the pyramid on your friend's screen.
Which leaves us with a pretty fascinating question to ponder the next time you connect to a network or load a web page. Think about this massive stack working flawlessly in milliseconds. Every single time you click a link, your data plunges through all 7 of these invisible layers, crosses the globe, and climbs back up to the application layer on the other side. But what happens when just a single link in this incredible 7-layer chain breaks? And honestly, how many layers were crossed just to stream this very explainer to you? Keep that invisible symphony of engineering in mind the next time you plug in. Until next time, stay curious.